Okay. Let's go over the questions very fast. First, the three questions are taken from midterm. So the first one is none of those protocols can protect data link layer attack, and IPsec can authenticate and encrypt both IP headers and IP payload. So the next one, the sequence number in TCP should be randomly generated, the initial number, for security reasons. And the question 3, port number is not part of the IP header. It's part of the TCP or UDP header. Question 4, the meaning of acknowledgement number. So the acknowledgement number is the next byte of a party expect to receive. The next byte, you just have to remember that. And when the TTL field reaches 0 and the destination has not been reached, a time exceeded error will be sent, not destination unreachable. So destination unreachable will be sent by the destination router, and the router knows this address is in the subnet I am in charge of, but I cannot find that IP address, so it's not reachable. So this one is B. And 6, a SYN packet consumes one sequence number, and an ACK packet doesn't consume a sequence number. So the next question is a SYN and ACK, so it consumes one sequence number because of the SYN part, not because of the ACK part. And the ACK number, it doesn't carry data, so it doesn't consume any sequence number. The last one, a SYN flooding, you did this in apps. So this is a denial of service attack, because it tries to consume the resources of the victim. Okay, so today and the next several classes, we will discuss a new networking paradigm called software-defined networking and the security of it. So this is a kind of new thing. It invented like, I don't know, maybe 10 years ago. Some people in academia has started talking about SDN, but the concept of SDN may only be there for 6-7 years. So before we talk about SDN, we have to look at the network structure of modern enterprise. And the very important thing is we need to redefine what is switch. So previously we talked about switch. We said that a switch is a data link layer device. Switches, they only look at data link layer headers. So they forward frames, and they use a switch table to map destination MAC address to an outgoing interface. And this outgoing interface is labeled with a physical port on that switch. So the switch table only has the outgoing interface and the MAC address that is collected with that interface. This is our traditional definition of a switch. So this is a switch table looks like. This is a switch. There are 4 ports, and each port, the switch table remembers which MAC address. This is a MAC address of host A, MAC address of host B. So how that physical port is collected to a host, to a MAC address. So this kind of switch, this traditional switch, is called a layer 2 switch, because they only look at data link layer data. And we also said that routers, they work on network layer because they look at the IP headers. So a router is used to forward data packets, IP packets, between different computer networks. So they look at the IP headers, IP source IP, destination IP. And the routers, they are also collected together. So a router will forward a data packet to another router, and how they know that other router exists and how they know the routes, they will use some protocols called routing protocols. So there are IGRP, OSPF, all kinds of routing protocols. So in this class, we didn't discuss routing protocols, but at least we discussed that there are routing tables in those routers. And whenever there is a packet comes in, a router will decide how to forward this packet based on the routing table. And that routing table can be configured statically. However, that's not scalable. So there are many dynamic protocols to compute those routing tables by each router. So each router will compute their routing table. And those protocols are called routing protocols. Those are the protocols we didn't discuss. However, there are many large enterprise networks nowadays and also a lot of data centers. So those data centers, for convenience, they have to divide those large enterprise networks into many sublets. Like the ASU networks, there are many different sublets. So one way to construct a large network like that is we use a lot of routers. So between each subnet, there is a router. So the router will forward the packet using the IP headers. However, it's very expensive and it's very kind of slow. Because every time a router receives the packet, the router will calculate the best route for it. So it's not the best practice. That's why several companies, I think it started from Cisco, they come up with the idea of a level 3 switch. So now our concept of a switch has been changed. So whenever someone talks about a switch, you have to ask them, you are talking about traditional layer 2 switch or layer 3 switch. And all our enterprise networks right now we are using, they are using layer 3 switch actually. So layer 3 switch is very similar to a router, but they are different. So first, layer 3 switch, it also looks at the IP headers, not only the data link headers. So the layer 3 switch and routers, they both forward based on IP addresses. But layer 3 switches, they are faster, but also cheaper than routers. We will see why later. However, layer 3 switches, they cannot offer all the functionalities of a typical router. So here is a basic comparison between layer 3 switch and a router. So for a router, it forwards each packet independently. So whenever it receives a packet, the router will decide how I want to route it. So it may go to different route to reach the final destination. So to do that, it will make a full router forwarding decision. And this can be very slow because it may lead to talk with other routers. However, the layer 3 switch, they usually will cache their decisions. So if it says a packet, it decides how I will forward it. Then next time it says a similar packet, it will use the same decision it made before instead of a dynamically calculated route again. So the benefit of this is it's faster, it could be cheaper. However, if there is a failure in the network, the layer 3 switch cannot find the best router at this time. It may not be the best route. It might be the previous best route. So the takeaway is layer 3 switch, they look at the IP headers as well. They kind of like routers. They also run routing protocols. So previously, the switches, you don't need to configure them. Every time you put a switch, you can use it right away. You don't need to configure. But it runs some protocols. It runs spanning SPT, spanning tree protocol. But we didn't talk about that because it's not really very related to security. So, but with ThreeSwitch, it's kind of like a router. So you have to configure if you want to manually set the routing table, or you configure use those routing protocols for this switch to compute the routing tables. So, and they are obviously layer 3 devices. So no matter we're talking about the switches and the routers, and at this point, the boundary between switches and routers, they are kind of blurry. And we are talking about two different functionalities of those forwarding devices. So basically, no matter it's a switch or it's a router, it has two separate functionalities. The first one is called the control plane. It's like the brain of this forwarding device. So basically, this functionality decides how to compute these forwarding tables. For routers, it means it will use routing protocols to communicate with other routers to decide what should be filled in this routing table for routers and L3 switches. For L2 switches, it means they will use a spanning tree protocol to learn the structure of the network and also construct the switch table. And another functionality is called the data plane. So the data plane only cares about when there is a packet arriving, and I will compare that packet with my routing table or switch table and just forward it. So it doesn't care about how that routing table or switch table was computed in the first place. So those are two different functionalities. And in our current enterprise network, it's very complicated. Usually, like ASU, we have a big router connect the ASU intranet to the internet. And after that, we have a lot of firewalls, intrusion detection systems, and many switches. And all of them are switches. They are not routers, but they are not L2 switches, but L3 switches. So they can support subnets. They can support a concept called VLAN, virtual LAN. So, but like we just said, all those switches, they have to be configured. So whenever one part of the network is changed, all the switches, they have to be reconfigured, or they have to dynamically compute the new routing table, everything. And every switch is doing that. They are distributed. So every switch is computing their own routing table. So this switch, it doesn't have a global view. It doesn't make global decisions. It only makes decisions for itself. And this has been a big problem. So first, it's expensive. A lot of IT has to be involved to configure those things. And the fundamental reason is they do not really separate the control plane and the data plane. So each switch, they are generating their routing tables, then they are doing the packet forwarding. So they should be two separate tasks, but they are mixed together in one box. So this box can be super complicated. First, it has a special hardware, not only our regular CPU. They use customized CPU, customized memory, and on top of that, each of them, they have to run an operating system. On top of that, each of them will run their own protocol. So this router may run the OSPF protocol, and this router may run a different protocol or different version of the same protocol. So if you want to upgrade your network, you have to upgrade each box because everything is burned into this box. They are not separated. So right now, the operating system part and those applications part or protocol part, they can be millions lines of source code. And the hardware part can be billions of gates. So they are all burned into this infrastructure, this box. So whenever you have to upgrade something, you have to upgrade all the switches. And if you want to try a new protocol, you have to change all the switches to make each of them support your new protocol, which can be very, very difficult. So the reason is, the reason this is difficult is the abstraction. There is no abstraction for the control plane. The control plane is in the switch, which makes each router or switch has its own brain to make decisions. So this is kind of like 50 years ago when we have computers in the first place. So we have everything, the computer software, the computer operating system, and the computer hardware, everything combined together in one box. So we do not have those abstractions and add a lot of middle layers to separate them. It's a very similar problem. So at that time, if someone wants to change his application code, want to read the tape, so his application code has to do that manually, to do that reading. So now you are using a lot of libraries, and that library will call the operating system's function to read files for you. So your application doesn't have to do everything. Your application doesn't have assembly code to actually read from the disk or memory. So this is how the networking guys, they come up with the idea of software-defined networking. So basically what they want to change is those closed, hard-to-change boxes with control plane and data plane. They want to separate them. They want to take the operating system out, the control plane out, and have something called the network operating system. And this network operating system has a global view of everything. It talks with all the switches. And on top of that, all those policies or the protocols can just be control programs on top of these network operating systems. So now the switches, they only have hardware. They only have that forwarding table. Either it's a routing table or a switch table. They only have those tables. They do not make decisions what should be filled in those tables. So now they separate, the idea is to separate the control plane and the data plane clearly. So the control plane will be the network operating system and control programs. So you can run different programs on this network operating system. It could be a load balancer. It could even be a firewall or intrusion detection system, which we will talk next class. And those applications and operating systems, they will decide what each of those switches should have in their routing or forwarding tables. So they will compute the routing table for each switch and forward that to each switch. Then each switch will only use that as a lookup table. Whenever a packet arrives, they will decide how do I forward this. So with the help of this, we have a global network view. So this was impossible before because each switch, at most, they know their labels. They know a brief idea what is the structure of the network, but they make their own decisions. When they make decisions, they do not negotiate with someone else. But now, because of this global network view, all the decisions are making at this centralized party. But even though this is logically centralized, they can be physically multiple isolated. So basically, this switch, this will separate the control plane and the data plane. So in 2008, this idea, I think it was proposed around 2006, 10 years ago. There has been several papers in the networking community and the security community talking about SDN. But at the beginning, they didn't use the name SDN. And around 2008 maybe, and maybe from this paper, this is the first paper talking about this operating system. And there are papers talking about how those operating systems can control the switches and what kind of abilities those switches should have. So we will talk about those issues in the next class. Okay, so this is all I have for the introduction of SDN. So if you have any questions? No questions? Okay, so next class we will talk about this part. Yeah.